now.
Yeah, so
It's
yeah, you
fine.
can be
It's fine.
reassured that it is me talking. So, but then sometimes the webcam is not, yeah, it's not working very well. Mm, mm.
Okay, so now we have over 50 people and it's 4 o'clock. Shall we start?
Yeah, sure.
Okay, let's start. Hello, everyone. I'm Zhen Taoshen from Nanjing University and the Secretary Child of
Mm.
ISEG. Welcome to ISEG webinar series. I would like to thank you all for your attending on behalf of ISEG President Professor Bing Shi and Secretary General Professor Chaoshen Tang. Today, we are very delighted to invite Professor Andy
Mm.
Leung as our speaker. Professor Leung is currently Associate Head and Associate Professor at the Department of Civil and Environmental Engineering, the Hong Kong Polytechnic University. He graduated from the University of Hong Kong for his bachelor and the University of California, Berkeley for his master, before he obtained PhD degree at the University of Cambridge, UK. His research interests include soil structure interaction, reliability of geotechnical and structural systems, probabilistic analysis approaches, and novel geotechnical instrumentation technologies. He has received various awards on research, teaching excellence, and knowledge transfer. Currently, he has been serving as the president of Hong Kong Geotechnical Society since 2022. His talk today is Adaptive Updating of Soil Properties through Monitoring Data for Improved Prediction of Excavation Response. Let's welcome.
Um, Thank you very much for the kind introduction. So, like I said earlier, I have to confess upfront that sometimes my webcam isn't working properly. So, yeah, if you don't see my face, I suppose it doesn't really hurt, because I believe you'll be able to hear myself clearly. So, right, so I'm sharing my PowerPoint file. Just want to make sure that everybody can see the screen. So, just like the chairman has introduced, the talk for today, the topic is going to be adaptive updating of soil properties through monitoring data for improved prediction of excavation response. So this work is actually based on the PhD study by some of my previous PhD students. So I'd like to share with you all some of our findings and the approaches that we are proposing in our group in Hong Kong. Okay, so right, so in today's talk, probably it will last for about 45 minutes. I've divided that into 5 parts, some of the background of why we want to do this, and then I'll briefly talk about the idea of characterizing the variability, or in particular, the spatial variability through the site data of the soil tests. And then I try to talk about how we propose to make use of the measurements of the response, the purple parts. We try to make use of the response data to help us understand the ground better and therefore to improve predictions of the system response. And then we'll be having 2 simple case studies for illustration, and then I'll wrap up with a short summary and my suggestions for the way forward. So let's get started with the background. Right. So I always like to start my presentation with this little diagram. This actually came from a survey in the UK, which was conducted um, to ask 28 construction managers about their projects. Basically, the question was about what usually causes the trouble when
Sorry, Andy, we lose your voice.
Oh, sorry, I probably pressed the wrong button. So
No, it's okay.
okay. So let's go back to this pie chart. So basically, what happened was that for those 28 construction projects, the respondents were saying that 22% of the respondents said that they had a problem with their project because they were not sure about the soil boundaries. And then some 20% of them said that they had a problem because they did not know exactly what were the soil properties. So this is quite interesting, but perhaps not really that surprising because as geotechnical researchers or practitioners, we know that for geotechnical engineering, most of the times the problem lies on the fact that we don't exactly know the material or their properties that we are dealing with. So obviously in our profession, we've got lots of nice equations, finite element model, advanced tools, and so on. But then if you don't know what parameters to use or what properties we are dealing with, then it's very hard to get the right prediction for our design purposes. So that's why I always feel like one of the main challenge that we want to address is the uncertainty related to the properties or the boundaries of our subsurface domain. So this was about the Hong Kong Shenzhen Guangzhou high-speed rail. So some of you may know that the terminus of this high-speed rail is in Hong Kong, the West Kowloon region of Hong Kong. It was actually planned, well, this project, this terminus, was actually planned to meet in 2015, but there was eventually a 3-year delay. It was opened in 2018. And of course, it was a very long delay, and the public was asking why. And the construction companies and the company, the MTR company, who was responsible for this project, they listed out several reasons why there was such a big delay. And then one of the important reasons that they cited was that the ground conditions was unforeseen. But then, right, I always feel like the ground conditions being unforeseen, maybe not that, well, it might not be really a new thing in our profession, just like what I suggested in the previous slide. So there have been quite a lot of previous studies that talks about the variability of material properties. So this table was taken from a very famous research paper by Professor Fun in Singapore and Professor Fred Kuhawi in 1999. So this listed some of the properties that many of us are familiar with: the undrained shear strength of fine-grained soils, and then the friction angle or the tangent of the friction angle for some silts or sandy materials. And I would like you to put your attention to this particular column, which talks about the so-called COV of the property. So COV, the full name or the full term of COV is a coefficient of variation, which is the standard deviation of that property divided by the mean value of that property. So if you look at this column COV, so you can see that the COV of the shear strength of soils can vary from 5% all the way to something like 80%. So just to reiterate the definition, basically, if you have 80, that means the standard deviation of that material property is as big as 80% of the mean value of that property. So in other words, that means there is a very large dispersion regarding the data that we can obtain for soil properties. So soil, rock, they are never uniform or homogeneous, and the heterogeneity or variations in parameters can be quantified by this value of COV. So, well, we know that if the properties are uncertain and variable, obviously that's going to have a big impact onto your prediction of the system response. So in our common practice, well, current common practice, whether it's in Hong Kong or elsewhere, I suppose that a lot of the times we take a lot or as much or as many soil sampling data as we can afford, and then we try to come up with some sort of moderately conservative estimates. And then during the construction project itself, we're going to take some field measurements, check against our predictions, and if the measured displacement, for example, if the displacement measurement is smaller than our prediction, then nobody worries about that anymore. So the data are cast aside if we don't run into trouble. That seems like a very common practice in the current state of the practice. But then the question I would like to ask in this background part is that can we make better use of the data, or it costs a lot of money to obtain those data? Can we use it more smartly and create more value from that data? And at the same time, everybody has been talking about AI, digital transformation in various fields of engineering. Can we use those data that we obtain during construction to continuously train our model so that the predictions can become more and more accurate or more and more realistic, reflective of the reality? So that's what I would like to address for the of today's presentation. So, well, to put it in a nutshell, we obtain lots of soil data before the construction, and actually we can use this data to quantify to the uncertainty or the spatial variation of material properties. And during construction, we can try to make use of the measurements data to give us additional hints or additional information to refine our model in a clever way. So we want to have a rational combination of these information so that we can make better judgments. And again, to put it in a nutshell, I'm going to come back to similar figures at various parts of the presentation, but then in simple words, we obtain these soil data, which might be from SPT, CBT, laboratory tests, to see that usually there is a lot of dispersion. And instead of just picking a conservative trend line, we can tackle this dispersion directly and use them to quantify the variability of the material. So I don't want to go into too much mathematics at this point, but I'd like to point you to some of the variables that we're going to keep talking about today. So in today's talk, this variable of Z is going to represent the data itself. So this one might be the strength of the material, for example, so by Z. And then the spatial variability, it will be defined by a parameter called theta. So basically, theta is going to represent the range of the variation of the material property. So I'm going to come back to this one in more details soon. And then after characterizing the spatial variability by theta, we're going to make use of theta to help us generate the so-called random field models. And then random field models are basically realizations or models of the subsurface domain where these different colors represent the difference in soil properties. So imagine you have a construction site where the shear strength of the material may increase with depth in general. So blue color may mean a smaller strength. Red color may mean a higher shear strength. So in general, the strength increases with depth. But then beside this trend, there will be local variations. That's why you see these different pockets of different colors. So that's what we mean by the random field model that represents properties varying in space. So these the first three figures are what we can do before the construction. And once we start the construction, we are going to have measurements of the response, which I'm going to represent by the vector or by the symbol y. For example, if you have an excavation, quite often you try to measure the deflection of your retaining wall. So this response can be lateral deformation of the wall. And we can make use of these measurements to update our understanding of the most realistic model. So that's what we mean by this figure. And then in the end, based on the knowledge that we gain from Y, we can update our model and then we can quantify how uncertain we are regarding the future performance for our system. So in this diagram, for example, this black line shows our best estimates of the system response. And we sometimes call it isotropy. In this case, on the right-hand side, you see that there seems to be several different layers of material. And so you can imagine in the horizontal direction, across the same layer, the properties should be more or less similar. So the horizontal direction So on the left-hand side, we say that the range theta of the variation is small. On the right-hand side, we say that the range
Sorry, Andy, we lose your voice again.
Sorry, it seems like my mic also sometimes doesn't work very
No,
well.
it's okay.
So sorry about that. So right, so we're still on this page. So we also sometimes try to represent or